Today we're going to start section 5.2, which is called the definite integral. And like I mentioned, we're going to be starting this from a little bit different perspective than sometimes this material is approached from the start anyway. And so the first thing I'd like for us to talk about is something called accumulated change. So suppose you had been driving, most of you drive, I think. So suppose you were driving for 2 hours at a constant speed of 65 miles per hour. How far would you have traveled? Say it loud. 130 miles. So what did you actually do in order to get 130 miles? Yeah, you just multiplied the time multiplied by the speed, right? And it was important actually that it told you that it was a constant speed for that to work, agreed? If you had a variable speed and you sped up and you slowed down, then you couldn't use the constant speed. You'd have to find sort of like an average speed that you went the whole time, agreed? So the idea behind this visually, and I know it doesn't really, this isn't a necessary step for this problem, I get that, but it's going to be more helpful into the more difficult problems we do for me to draw a picture of what's going on. So imagine that you were driving at the constant speed, like we said, of 65 miles per hour. If you were doing that, oh, it left you. Okay, just a sec. All right, so if something is a constant function, what does a constant function look like when you graph it? It looks like a line. What kind of line? Okay, the lines are automatically straight. There's another word we want. Horizontal or flat. Okay, a horizontal or a flat line is actually a constant graph. So we're going to draw a horizontal or a flat line, constant graph, at a height of what? 65, because that's what the problem said, right? 65. And we're going to do this for a span of 2 hours. All right? So when you're actually finding this quantity that we just found a minute ago, what you're finding is you're finding a what? An area. You find the area of a rectangle is what you're really finding. The width was 2. I know this is not drawn to scale, but the width was 2 for the 2 hours, and your height was the 65 for this constant speed that you were driving. And so you're actually finding an area when you're finding the answer to that question. At least that's a visual representation of what you're finding. So when we did this, we said it was 2 times 65 for 130, and it would be miles, right? And what we're finding is an area. So, I can't remember if I wrote this down or not. Oh, here it is. So for a rate of change in this idea, that's what the speed that you were driving is. It's a rate of change. Okay? For a rate of change function f prime of x, we can find the area under the curve from A to B. Ours was from 0 to 2 for 2 hours. And this finds the change in f of x from A to B. In our case, the change in the miles that we've driven. How much further away we are from where we started. So jot that down. It's an important fact. We're finding an area under the curve from A to B. Now, it was really nice that it was a rectangle, wasn't it? And it was a rectangle because it was a horizontal line. If it had been a different type of line, we still might be able to find the area. That would be okay. But if it were a curve, quadratic, something like that, that process doesn't quite work so well. Agreed? Because it doesn't look like a rectangle. So that's what we're going to look at next, is we're going to look at what happens when the function's not a horizontal line, when it can't be done with an actual rectangle. Did everybody get this one written down? Okay. So for non-horizontal functions, what you can do is you can approximate the area by using multiple smaller rectangles. So we're still going to use rectangles. We're just going to use more than one of them. You're cringing over there. Why are you cringing?
I don't like this part.
You don't like this part. Caleb already is telling us he doesn't like it. Let me draw you a picture at least of what's going on. Okay, this is going to be our function. Actually, let me make it a little bit more curved because it'll be easier to draw. Okay, this is our function. And we're going to put A here and B over here. And if I draw lines vertically up to the curve itself, my curve did not quite go high enough, so pretend. We're trying to find the area of that region, and it is definitely not a rectangle. Agreed? Yeah, definitely not a rectangle. But what we're going to do is we're going to split it into sub-intervals, the smaller pieces of interval. I'm going to draw 4 because 4 is the easiest one when I split things apart to draw. And it gives you the same idea no matter whether I draw 4 or more. So there's 4 rectangles, at least there's 4 widths that are supposed to be roughly equal length. And we somehow have to get a height. And the height's the tricky part because the height on the left, the height in the middle, the height on the right, none of the heights are the same. At least they wouldn't have to be. So there's actually some different ways that we can find these heights. So for just now, I'm going to use the location for the left side as my height on each of these. And I would have these 4 rectangles just so I can draw one. Okay? So the notation for what we're doing, a starting point and an ending point and finding this area under the curve, looks like this. It's got this sort of long script S. It has the numbers A and B, the starting point and the ending point at the top and the bottom of the script S. We put the function name, whatever it is. I'll call it f of x for this one. So this function here is f of x next to this script S. And we put a dx on the end. And what this is, I'll tell you how we read it, but what this is it's the area under the curve from A to B. Okay, so let's actually talk about how we read this. I mean, because I keep using the phrase script S, and that's totally not a mathematical phrase at all. That's my made-up language. I just made it up. Okay. What this is actually called a definite integral. If you notice, that's the title of the section, the definite integral. This is the definite integral from A to B of f of x. The dx at the end simply tells you that the variable in the problem is x. It's kind of like we go, when we were doing the derivative notation, we did dy dx. You remember that derivative notation? And I talked about this dx means with respect to x. X is the variable. And again, for what we're doing with calculus right now, that seems like a duh kind of statement. I mean, you know it's with respect to x or t, whatever the variable is we're using, and it's usually one of the two, because it's always with respect to that variable, right? The kicker is that when you take advanced calculus, just like a calculus section beyond this, and it's actually in our book, if you were at OU and you were getting the major you're getting now, you'd have a 2-semester calculus, business calculus sequence. And they go further into this book, and they do calculus with multiple variables. And this dx at the bottom becomes much more meaningful in that context. So that's the reason for using that in that way, okay? So it's not meant to sort of make a mess of things. It's actually meant to clarify things into the future, right? So that's what it's for, is to tell us that the variable is x. All right, so we're going to do an example. This whole section is going to be interpretation. And then the next example, I should say, is going to be interpretation. And then I'm going to actually do the part that Caleb doesn't want me to do, where we're actually going to find these areas. Okay? So here's our first example. When warm water is released into a river from a source such as a power plant, the increased temperature of the water causes some algae to grow and other algae to die. In particular, blue-green algae that can be toxic to some aquatic life would be one of those examples. If A of C is the growth rate of the blue-green algae in organisms per degree Celsius, and C is the temperature of the water in degrees Celsius, interpret the following in context. So let's actually take a look at what we've got. We've got some notation on your paper as well. This is the definite integral from 25 to 35 of A of C dc. Okay? Now what I just said out loud is not an interpretation. It's just how you read that. The interpretation has to do with what all those numbers mean in the context of the problem. Okay? So let's start with the 25 and 35, and let's just identify the pieces before we start writing any interpretation down. What are the 25 and the 35 in this problem? Yeah, they're the temperatures in maximum and minimum temperature in the degrees Celsius, right? So the temperature is changing. They're putting additional water back from the power plant into the river, and the temperature is going from 25 to 35. That's what that says, right? Okay, so what was A of C? Should move back over here. The growth rate of the blue-green algae. Okay, this particular type of toxic algae. And what was C? because it says DC with respect to C at the end. The temperature of the water. Okay, so we know that the water is what's changing temperature. That's the 25 to 35 that we had, and that's how we're going to start. Anytime we're doing interpretation with these, we're sort of moving from left to right. So what we have is the change in the algae from the temperature. So this is what's changing. Actually, I'll start it with what I just said. I'm totally going to make a mess of this. When? That's the word I want. No more rewriting. When. When the temperature changes from changes, or you could say increases because it's an increased change, but it changes from 25 degrees Celsius to 35 degrees Celsius. This represents, or this is, what? It's the change in what? This is the change. Change in blue-green algae, or the number of blue-green algae. Organisms. Yeah, that's it, because the organisms per degree Celsius was the rate. So when the temperature is changing, this is the change in the number of blue-green algae. So back on our problem originally, if we were to do the same thing, right, our integral over here would be the integral from 0 to 2 of 65, we'll call it dt since it's time, right? 0 to 2 hours, the function was actually the function 65, and it was dt because the time was changing. That's the notation that would go along with what we were doing before. Now, on part B, we're going to do the same thing. We're still writing a descriptive change over here. But instead of giving it to us with the mathematical notation, the derivative, or the integral notation, definite integral notation, they're actually giving it to us in words. This actually describes the area of the region between the graph of A and the C-axis from 30 to 40. So what I'm going to write down is going to look an awful lot like what I just wrote down. I'm going to start out with when the temperature changes, okay? But what are the numbers that I'm going to use instead? 30. Yeah, the 30 and the 40. So when the temperature changes, from 30 degrees Celsius to 40 degrees Celsius. This is the change in the number of blue-green algae organisms. So some of the questions that you're going to do in this section are going to look like this. You're just going to be writing down a sentence about how things are changing. Okay, we did this when we did derivatives too, right? We had some questions where all we're doing really is just doing an interpretation. That's all it is. Okay? All right, so we're going to switch gears a little bit, and we're actually going to find out how we mathematically compute these areas when we're given an equation. So that's what we're looking at now. All right, so there are two types of, well, I think there's three, but two on this page, yeah. Two types of rectangles that we could look at that are the simplest to do. They are left endpoint and right endpoint rectangles. So imagine drawing the same picture that you had drawn before. So I'd like for you to sketch two pictures. One, we're going to label one left, and we're going to label one right. and you're going to draw two roughly equivalent graphs. They don't necessarily have to be the same as the graph I'm drawing, but you're certainly welcome to make them that way if you'd like. Whoops. You're going to mark an A and a B on them. I'm totally going to do this a little bit different. And you're going to draw 4 rectangles inside. Again, there's nothing special about 4 except that it gives us enough information without overburdening in our picture and making it look very difficult. Okay? So this is my picture. I'm going to copy paste it.
Does it matter where you put the A and B in?
Not for what we're talking about now. It will in general in a problem because it'll give you an A and a B value like concrete numbers. But for what we're doing right now, we're just getting an approximation for a picture. That's all we're doing. All right, so in the left picture, the first one that you drew, we're going to use the left-hand corner as the height for each rectangle. So as you're taking a look at these, the left-hand endpoint, that was not so good drawn, let me try that again, is the height. So in some cases, the left-hand endpoint means that the rectangle is actually under the curve, and in some cases, it may actually be slightly above the curve. On your second picture, you're going to use the right-hand endpoint of each rectangle to give you the height. And obviously, you get a different set of rectangles. And in the graphs that we drew, it's actually the case that the first one has most of the rectangle space underneath the curve. And the second picture has most of the rectangles actually extending above the curve. That doesn't always happen. It just depends on the graph that you're working with. And what I want you to do is go ahead and shade in those areas that you have created rectangles to represent. Again, you're shading the rectangles, not the actual curve. So the area is shaded inside of the rectangles, so it may or may not actually be inside of the curve. It may not capture all the area that's inside the curve, but it is the interior of the rectangles.
Can you explain to me why on the left graph you went under on the last line?
Oops. Yes, on the left graph on the last line. Yeah, so these two are my endpoints, and the left one is going to be that one. Of those two, that's the left-hand side, so that's the corner I use to make my height. Whereas over here, my two endpoints are here and here, and this is my right one, so I'm using the right-hand endpoint to make my height. That's what I'm doing. Okay, and there's one other way we can do this, we'll do it in a minute, but the left-hand and the right-hand endpoints are the simplest options. What I'd like for us to do is actually give names for each of these interval locations, like the x values. We're going to call this A value x0, and then the next one x1, x2, x3, and then the B is going to be x4. And we'll do the same thing below. A is x1, 0, excuse me, and then x1, x2, x3, and x4. Okay. So we're just making a list of subscripts. You could call them 1 through 4. It wouldn't hurt anything, but I don't want you to think that they have to be the numbers 1 through 4. But they usually are evenly spaced. As when we create them to be evenly spaced for a better approximation. All right, so tell me, you did it on the first page. How do we find the area of a rectangle? Base times height, length times width. One of those two versions is probably what you've done your whole life, right? So if we're taking a look at the first rectangle, I'm going to point at the lower one because I can reach it better. If you're taking a look at this particular rectangle right here, the width is this piece, correct? All right, and so I should be able to say, okay, well, that's like x1 minus x0. Okay, we're going to give it another name in a minute, but it's the distance across here. And that's why it's going to be convenient for them to all be the same, is so that we can actually have one name for all of them. And then the height is going to be different depending on which rectangle I'm at, right? So the height on this rectangle is right here, but the height on this rectangle is here. All the heights are different. Everybody good so far? So we need to know the height of each rectangle, we need to know the width of each rectangle. So what we do for the width is we're going to call the width delta x. Delta means what? Do you remember? Change in. Because this is the change in the x values. And if we've evenly spaced them, they're all the same delta x width. So far, so good? Now, the unfortunate thing, of course, is that the heights are, in fact, all different. So let's take a look at how we determine the heights. Let's look at the very first picture, the left-hand rectangles. As you're looking at that very first left-hand rectangle, if we use the left-hand side of it, so I'm thinking about this piece right here, and I need to know what the height is of the rectangle at that location. That's actually a y value for the curve. This equation has there is some equation, y equals f of x, right? And so there is a y value that's associated with it. So like this point that this location where I'm pointing at, oops, I meant to get the eraser. This location is an xy pair. It's x0, y0. That's that corner. It has an ordered pair point. And the height is the y value. Okay? Now, we don't usually use y0. We usually use the function notation. So the notation that we're actually going to use is f of x0. That's this cornered point right here. And that's the height of the first rectangle. Now, the second rectangle height, though, is similar, yeah? It's this point. What would be the height of the second rectangle? Yeah, it would be the f of x1. It's the y value at the x1 coordinate. And then the third one would be the y value at the x2 coordinate. And the fourth one, I've kind of got a mess on my picture now, right here, is the y value at the x3 coordinate. There are 4 heights, and they're all just different y values along this function. So literally what we have is we have the first area is the width, delta x, times f of x0. This is width, this is height. So base, if you will, times height. That's what you have, base times height. Oh, I put base times base. Base times height. There we go. That's the first rectangle. The second rectangle is also a base, which is delta x times the height. What's the height? F of x1. The third rectangle is the width, delta x, times the height. What's the height? F of x2. And the last one, let me make this a little bit smaller so I have some more space. The last one is the same width again, delta x, times the height, f of x3. Now, these are 4 areas here that we're adding together. They're all base, which is delta x, times the height, which is a y value. But take a look at it from an equation standpoint. What does each component of this sum have in common? Delta x. So instead of doing all of this multiplication, we're going to factor the delta x out in front, and we're simply going to add up the y values, f of x0 plus f of x1 plus f of x2 plus f of x3. Instead of doing 4 multiplications and adding 4 quantities together, we're going to add 4 quantities together and multiply once because it's faster. That's why we're going to do it that way. It's easier to do, fewer mistakes to be made. Now, if I follow that same pattern, take a look at the second picture. What are the heights of these rectangles? What about the first rectangle now? Instead of using the left end point as the height, I'm using the right end point as the height. So what's the height of the first rectangle in the right rectangle picture? It's actually f of x1. So this height is f of x1. What's the second one? F of x2. The third one? F of x3. And the fourth one? F of x4. So when we're calculating the heights, or calculating the areas of the second rectangle, we can use what we've already discovered to know that we're going to be multiplying them all by delta x. And we're adding 4 heights together, and they are f of x1, f of x2, f of x3, and f of x4. Okay, so left endpoint, right endpoint, one more picture after this. So jot the rest of this down on this slide, and then I have one more picture to show you, and then we're going to do some concrete examples, actually. Okay, so we have left endpoints, we have right endpoints, and the other option here that we look at is the midpoint, something somewhere in between. So I'm going to try and see if I can get my same graph that I had before. Good, it was still saved in there. And we're going to use the midpoint of each location as our height. So if you imagine taking the midpoint and doing sort of like a dotted line up to the curve. And that dotted line up to the curve is going to be where I draw my height at. So if you imagine there's the first one. Here's the second one, the third, and the fourth, roughly. That's a little bit low. And we're going to shade them in just like we did before. All right, so when we actually go through computing these, that means we actually have to find another in-between point to find the height at. For what we're doing right now, we're just going to label these x1, x2, x3, and x4. They're not the same x1 through x4 I had on the previous slide, but they've got to have another name anyway, so I'm just going to use the same numberings that I did before. Notice the same widths occur, right? It's still delta x for the base. So the way that we calculate the area is still delta x times 4 quantities, 4 heights, and I've labeled them f of x1 to f of x4. Any questions so far? There's nothing special about my numbering. I could have labeled them 1, 3, 5, 7, 9, kind of, that would be fine too. It doesn't make any difference, but that's just what they're labeled. All right, let's do an example of one actually. Okay, the rate of change in the percentage of low birth weight babies, those are babies weighing less than 5 pounds 8 ounces, in 2000 can be modeled by this equation, percentage points per pound, where W is mom's weight gain in pounds. So the first thing we're going to do is we're going to sketch a graph of the function P from W equals 18 to W equals 43. So grab your calculator, put the equation in that they were giving you. Yes, into Y1 is fine. Okay, and our window is supposed to go from 18 to 43. So after you put the 18 and the 43 here like this, hit zoom 0, and that will pick a good viewing window for the Y values based on the X values. Now do you see the dotted sort of line, if you will, at the top of your screen? Does everybody have a dotted line like that? That means the X-axis is up there, but it's not quite right there. If you hit window, you can actually see your Y max right now is at negative 0.017. I mean, it's really close to 0. If you want, you can actually make it 0 just so that you can actually see the solid line filled in up there. That is your X-axis. So this is the graph that we're looking at sketching on our paper, okay? So go ahead and sketch this graph onto your paper. And you know from the graph that you're starting at 18 and you're going to 43. So those pieces should also be present on the graph that you're drawing. So we're going to go from 18 to 43, something like that, on our sketch. A couple questions it's going to ask us. Yeah. The first one says, what does the fact that the graph of P lies below the W axis from W equals 18 to 43 tell you about the percentage in low birth weight babies since 2000? What does the graph being below the axis mean? It's negative, okay. This is actually, remember, this is in percentage points per pound, so it's a rate of change. So what does it mean for a rate of change to be negative? It means that the original graph is decreasing, okay? So go back to the way they phrased the language over here. It says that this is in percentage points per pound. W is mom's weight gain in pounds. So this is telling you that as mom's weight increases, so like this 18 means mom gained 18 pounds, the 43 means mom gained 43 pounds, okay? So what's happening to the birth weights of the babies as mom has gained more weight as opposed to less weight? The birth weight's not as low. There are fewer low birth weight babies, right? Because this is supposed to be measuring the number of low birth weight babies. So there are fewer of them based on how much weight that mom has gained. Does that make sense? The original graph is decreasing because this is the derivative graph, right? This is the rate of change graph, and the rate of change graph is negative. So the original graph would have been decreasing. Okay, so let's write that down. I will write it in a concise form, something like this. As mom gains weight, or as the mothers have more weight to be gained, or something like that. As mom gains weight, the percentage of low birth weight babies decreases. All right, and the last example is actually what we're going to calculate. C says it wants us to find, or to use, 5 midpoint rectangles to estimate the area of the region between the graph of P and the W axis from 18 to 43, and then to interpret our answer. So here's our graph. Whoops, I went too far back, didn't I? There we go. There's our graph. And we're going to make 5 rectangles. So the first thing we have to do is we have to figure out where we're going to draw these lines for these rectangles. So how far is it from 18 to 43? 25. Okay? And I want to make how many rectangles? 5. So how wide is each rectangle going to be? 5. So in some sense, this is what we did. We said that our delta x, I'll give you a formula for it if you'd like. It's b minus a over n. B and a are the endpoints. N is the number of rectangles. Question, Brock?
How do we know how many rectangles to make?
It told us on part C. Do you see it?
Oh,
Yeah.
yeah.
It'll have to tell you somewhere, otherwise you don't have a clear indication. Yeah, it'll tell you at some point in the problem. So for this one, we had 43 minus 18, and we had 5 rectangles. So we end up with our delta x actually being 5. That's important information because that's part of our equation, right? Our equation means that I'm supposed to be taking this delta x times the sum of the heights. And you just found out that your delta x is 5. So in some sort of sense, that's like half the work. It's the shorter half of the work, so probably half's not the right word. Now we got to find the heights, okay? And that's the part that Caleb loved so much, I can already tell. All right, so here is a rough guess on our rectangles. So let's actually label all of them. We know they're all 5 apart. So what comes after the 18? 23, and then 28, and then 33, and then 38. Those are them. What kind of rectangles did it ask me to make, though? Midpoint. So do I really actually use any of these values right now? Not really. I need to know the in-between value for each of those rectangles, yeah? I need to know what's halfway between 18 and 23. And unfortunately, in some sense anyway, it's actually a decimal. Because I'm dividing by 2, and it's 5 wide, right? So what's halfway between 18 and 23? 20.5. What's halfway between 23 and 28? 25.5, right? What's the next one? 30.5. They're going up by 5s. What's halfway next? 35.5. And the final one is 40.5. These are the heights that I need. Now, they aren't heights, they're the x values, but they're the x values that determine the heights. So if you take a look back over here, what I'm going to be finding is, what was the name of my function? Was it p? Yeah, it's p. I'm going to be finding p of 20.5 plus p of 25.5 plus p of 30.5 plus p of 35.5. I need one more, right? Plus p of 40.5. All right, so the cool thing is that your calculator can do all of that for you. So I'm going to say, like, go calculator, yay. That's like good news, right? So grab your calculator. Let me show you how your calculator can be useful for this task. Okay, we already have the equation in y1, agreed? And we want a whole bunch of heights. All right? So what we're going to do is in your regular screen, come back over here to your regular screen, clear it out if you want to. What we want to do is we want to tell it that we want the function evaluated at these different points. And you have a feature that allows you to do that. We've been using this button called vars for a number of weeks now, right? Months even. Vars, yvars function y1, and we can put a parenthesis next to it and we can tell it 20.5. What's even better is that we can add them all together in the same line. We don't even have to know them individually. So I've got y1 of 20.5 plus y1 of 25.5 plus y1 of 30.5, and on down the line until we get to the last one. I know it kind of wraps funny, and I know some of yours just keep going along the same line across the screen. Doesn't matter. But you should have 5 data values. For every parenthesis you open, you should close one. Do all of your screens look like that? Now that's almost what it asked me to do here, right? What am I missing from the actual equation or the calculation that I'm trying to do? The multiplying by 5. And you could do that on this part too if you wanted to, but I think it's probably just easier to hit enter and then times 5, just so I don't have to worry about all the extra parentheses and whether or not they're there and appropriate. So the correct value that I get then is the negative 4.818. What are the units on that? Negative 4.818 what? What were the units on the function originally? Percentage points per pound, right? Those were our original value. Do you remember when we did the problem at the very beginning that was the miles per hour? And then we multiplied by the number of hours and we ended up with miles, right? How many miles we had driven, agreed? The same thing's happening here. We're calculating area. One of the units for area is percentage points per pound. Okay, that's the y values. This is in percentage points per pound. What is my x-axis in? It's in pounds. So what happens when we multiply percentage points per pound times pounds? The pounds goes away. It cancels out, just like the miles per hour. The hour canceled out when we did the very first problem. We end up with the percentage points. So my units on this is percentage points. Now there's one more piece of this that you have to do. One more thing you have to do on this problem. What is it? Yeah, they interpret your answer. I'm sure. I know, it was there. If it's not there, you don't have to do it. So don't go making more work for yourself. But if it's there, you're going to do it. All right? Interpret your answer. What does that mean? Well, it means it's going to look a lot like that blue-green algae problem. All right? So what happened on my x values? What changed here? The pounds from the birth weight, or the weight that the mother gained, right? It was the weight that the mother gained that changed. And so we're going to have that part in there, that it went from 18 pounds to 43 pounds. Okay, that's going to be in there. What's actually changing in the problem, though? The percentage of what? The low birth weight babies, right? How many babies are low birth weight? That's actually what's changing. So we're going to have all those pieces in there. I'm going to start this out a little bit differently than the other one, not because it matters, but just I want to help you see a variation. We're going to start with, as the mother's weight gain increased from 18 to 43 pounds. Okay, that's the time frame. That's over when this change happened. When the birth weight, or when the mother's weight gain changed. The percentage, let me say it that way, chance of a low birth weight baby decreases by 4.818%. Yeah, you can. It's kind of the same meaning, but if you want to be more clear, definitely you can.